All right, let's make two of the fundamental definitions for this lecture. So the row space and the column space. So we'll let A be an m by n matrix. So that means it's got 1, 2, 3, blah, 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 m rows, and it's got n columns. And so the row space of A, it's the subspace of, let's say, Rn, spanned by the rows of A. So if you think of each one of these things as row vectors, right, what's the span of those things? That's the row space. And then the column space of A, it's the subspace spanned by the columns of A. So you think of each of the columns now as a vector. And so the space spanned by those columns is what we'll call the column space. Let's look at an example really quick. All right, here's a 4 by 5 matrix. And so what is the row space of this matrix A? Well, it's the subspace spanned by 1, 2, 3, 4 columns, right? So there's 1, 2, 3, 4 rows. These are row vectors. Although I don't have enough room on the board to write them as row vectors, so I'm going to just write them as column vectors. So these 1, 2, 3, 4 rows give us, the span of these 4 rows will give us the row space. And you can notice that each one of these vectors in the row belongs to R5 because each row has 1, 2, 3, 4, 5 entries. That's the same as the number of columns. So the row space lives in R5 because that's the number of columns. So just don't get those confused. And now, what's the column space of A? Well, it's the subspace spanned by the columns of A. 1, 2, 3, 4, 5. So there's 5 columns. There's 5 columns. And so the span of these 5 vectors is going to give us the column space. And notice that each one of these columns lives in 1, 2, 3, 4, lives in R4. So the R sub m, right, that's going to be the number of rows. So that's where the column space lives, right? It lives in R4, which is the number of rows. So now we might like to find the dimension of the row space, or we might like to find the dimension of the column space. We're going to do that for this example. As it turns out, those two, the column space and the row space, should have the same exact dimension. And so once we see what that is, we're going to name the rank after that, after those two equal dimensions. All right, so we want to find a basis for the row space and the column space. Let me just go ahead and find the basis for the column space first, just because maybe the layout is already familiar. So we've got this matrix A, and we're looking at the span of these 1, 2, 3, 4, 5 vectors, right, in R4. So how do we find a basis? How do we pick out a basis from these 4 columns? These 6 columns in R4. Well, we take the columns, like based on the previous 2 examples, take the columns, arrange them in a matrix, put that matrix in reduced row echelon form, and then we saw that the vectors associated with the free columns, those are the things that are going to be linearly dependent on the pivot columns, right? So when you take this thing, arrange it in a matrix, and then take that matrix and put it in reduced row echelon form, you can see that 1, 2, 3, the first 3 columns are pivot columns, and the last 2 are free. So we would let S be 0, T is equal to 1, and then S equals 1, T equals 0. That would show us that these last 2 vectors, right, these free vectors, are linearly dependent on the first 3 pivot ones. So we know we can rule these 2 out, right? They're associated with the free columns. We can rule those out. And so now a basis for the column space just consists of these 3 vectors, right? So the dimension of the column space is equal to 3. So now we want to go ahead and check, find a basis for the row space. So we found a basis for the column space. It's the first 3 columns because that was associated with the first 3 pivot columns, right? and we got rid of the two free ones. So these were both free, get rid of them. Now we want to do the same thing for the row space. All right, so here's our 4x5 matrix A. We found the column space was just generated by these three columns, right? So all of the columns can be written as a linear combination of these three columns. So we saw the dimension of the column space is 3. What is the row space? What is a basis for the row space? So let's take the rows 1, 2, 3, and 4, and we've written them down as vectors, as column vectors. It doesn't make a difference. I just didn't have any room to write them out as rows across the board, so I've written them as columns. And so now, how do I extract a basis from these 1, 2, 3, 4 rows? 1, 2, 3, 4 rows. Well, take these vectors, arrange them in a matrix, put that matrix in reduced row echelon form, identify the pivots and the frees, right? So we've got pivot, pivot, free, pivot. So that tells us that we need to get rid of this third vector, right? So we get rid of this thing, meaning we get rid of the third row. So that means these three rows, 1, 2, 3, these three rows make a basis for the row space. And so now we can see that the dimension of the row space is equal to 3. And remember, this was the same as the dimension of the column space. So that's no accident. So that's going to be a theorem, and we'll state that formally now. All right, let's tie together all of the stuff that we've seen from these previous examples. So let's let A be an m by n matrix. The row space of A, it's the span of all of the row vectors. So those row vectors live in Rn. And remember, n is the number of columns. So the row space is a subspace of Rn, where n is the number of columns. The column space is a subspace of Rm, where m is the number of rows. The dimension of the row space is always equal to the dimension of the column space. That's what the last example suggested, right? We computed the row space and the column space of a 4x5, and we saw that the dimension of the column space was 3, and the dimension of the row space was also 3. Now, the row space lived in R5, right? So it was a three-dimensional vector space in R5. This thing was a three-dimensional vector space in R4. So even though these row space and column space live in different ambient spaces, they will always have the same dimension. So the dimension of the row space is always equal to the dimension of the column space. And so now we'll make a definition. The rank of a matrix A is just the same thing as the dimension of the row space, or if you like, it's equal to the dimension of the column space. And we saw that the dimension of these things, right, the dimension of a spanning set, or a vector space spanned by a set, it's just the number of pivot rows or pivot columns of an appropriate matrix. So in this case, right, to find the dimension of the row space or the dimension of the column space, just put the matrix in reduced row echelon form and then count the number of pivot columns, which that'll be the same thing as the number of pivot rows, which is the same thing as the number of non-zero rows. So when you take that thing and put it in reduced row echelon form, the rank turns out to be the number of non-zero rows of the reduced row echelon form. So this is also equal to the number of non-zero rows of the reduced row echelon form of A. You could stop at the row echelon form of A, but really the reduced row echelon form is going to tell you everything you need to know.